All right, so today we have Craig Lawrie. Tell us about Higgs, Coulomb, and Hall Littlewood. Take it away.
All right, thank you for the invitation to give this nice talk. This has been one of the highlights of the pandemic has been this particular series, so I hope it long continues. No pressure, Julius. But I'm very excited about this meeting and I'm very happy to be able to talk here. So today I'll talk about some work that's came out over the course of the pandemic. In principle, these 3 papers with my co-authors Monica Kang, Jaewon Song, and then the second paper also with Ki-Hong Lee, and the third paper also with Mateo Saki. So, okay, there we go. And you can see this nice picture of us all enjoying collaborating together on Zoom. So for this audience, I don't need to give too much motivation, but let me give a very brief motivation anyway. So perhaps you're interested in quantum field theory. Quantum field theory is a very powerful framework that can be used to answer questions in all sorts of areas of physics, not just high energy theory. But as we all know, quantum field theory is typically hard to study, except for maybe in some perturbative regimes, you know, around some Gaussian fixed points of the theory, etc., etc. So if we want to study QFT, one of the things that we can do is that we can add some new symmetries, and adding these new symmetries can make hard questions more tractable. That's the usual philosophy in physics. So one symmetry we might want to add is supersymmetry. Supersymmetry tells you that there are some quantities which are then protected from quantum corrections. So that sounds great, something we could perhaps compute. And we might also want to add conformal symmetry. So conformal symmetry sits at the fixed points of renormalization group flows between QFTs, as I've drawn here. So yeah, but as you can see, this rather decreases the size of the space that we're studying. But let's study this particular subspace of SCFTs. Okay, so if I give you a 4-dimensional superconformal field theory, one of the things that happens is that if I put the theory on a curved background, then the conformal symmetry itself becomes anomalous. And that anomaly is basically captured by 2 numbers. And those 2 numbers, those are what are called the central charges, C and A, and they appear in the correlation function of the stress energy tensor in this way. So they're the coefficients of the Weil tensor and the Euler density, which are just defined by the choice of background that you put the CFT on. And these numbers are pretty interesting. So you can consider them like an invariant of the CFT. If these 2 numbers are different, then your 2 CFTs are different. If they are the same, then maybe your theories are the same, maybe not. But they're more useful than just this. And one reason for this is something called the A theorem. So the A theorem tells you that if you start with a theory in the UV and it has some central charges, A and C, and then you do some renormalization group flow to some new theory with some new central charges, A and C, then the A theorem tells you that this quantity A always decreases. It's worth noting there's not an equivalent statement for C, but A always decreases. So since we know that doing a renormalization group flow is kind of like integrating out some degrees of freedom, we can think of this quantity A, the central charge, as measuring the degrees of freedom of that theory. Okay. There are more things you can say about the central charges. So for example, unitarity fixes that the ratio of the central charges is rather tightly bounded, somewhere between 1/3 and about 2. This is work by Hoffman and Maldacena. So a long time ago. So the lower bound is saturated by the theory of a free scalar field, and the upper bound is saturated by the theory of a free vector field. Okay. And if we add supersymmetry, then these bounds, in fact, become a lot stronger. These are the cases with supersymmetry. So if you have n = 1 supersymmetry in 4 dimensions, the lower bound is now saturated by the free chiral multiplet, which is then 1/2, and for n = 2, it's the free hypermultiplet. So these are sort of natural generalizations of the free scalar field in a non-supersymmetric theory. And while I can't see it because I can see your videos instead, but why don't let's see. I can minimize this Zoom box. Okay, great. Now I can see my own slides. So on the right, the upper bound is always saturated by the free vector field. Okay. So I've told you about some properties of superconformal field theories in 4 dimensions. They have central charges. These central charges measure the degrees of freedom, and there are some bounds on what are the allowed values of these quantities. So this is a good time to say that I encourage you, if you have any questions, to jump in at any time. I'm more than happy to do it like this. Okay, great. So now that I've told you a little bit about the properties, let's now be more concrete and talk about some actual 4D SCFTs. Like this. So the class of SCFTs that I'm going to consider today, they go under the name of class S, and they come from sort of 2008, 2009 papers of Gauro and Gauro-Murnitsky, and you can write them in this nice colorful form. So they start by considering the 6D 2,0 superconformal field theory of type G, where G is some ADE Lie algebra. So these are 6-dimensional theories that you can engineer by compactifying type 2B string theory on an orbifold. These theories are, ubiquitous, and they probably need no further introduction to this audience. Okay, now there's this object CGN. So this is that you take the 6D 2,0 theory and you perform a twisted compactification on an n-punctured genus G Riemann surface. Now, if I tell you that there are n punctures, I have to tell you what a puncture means. And that requires some data, which is this thing that I put in the green braces here. So typically, punctures are associated to nilpotent orbits of the ADE group that you start with, but not exclusively. And I'll fill more in on what this means later. And if you put all of these ingredients together, you end up with a 4D n equals 2 SCFT. And this is a rather useful construction because complicated physical features, like S-dualities that relate strong and weak coupling, shall we say, versions of the same theory, are sort of explicitly captured in the geometry of this Riemann surface. So in that sense, you access highly non-trivial physics just by knowing that it comes from 6 dimensions. Okay. And more so than this, each punctured Riemann surface has what's called a pair of pans decomposition. This you can just imagine by looking at this picture of a genus 2 surface and just stretching it apart until it's just 2 balls connected by long, thin tubes. You can see that this thing and this thing are topologically equivalent. And so what you can do is you can think of taking a collection of 3 punctured spheres and glue them along the punctures. So then, once you understand the 3 punctured sphere theories, and once you understand how to glue theories, you understand everything. So these 3 punctured sphere theories go under the moniker of the Tinker Toy theories, and they have been studied in great detail over the last 10 or so years. So the point to make here is that class S theories can be constructed from relatively simple building blocks, those being the 3 punctured spheres. Okay, so I've told you a little bit about one aspect of the 4-dimensional n equals 2 superconformal field theory landscape. So let's just draw a bigger picture. So there is this class S part of the landscape that I've just told you about. There is another interesting part of the landscape that also comes from 6 dimensions, this time from the 6-dimensional 1,0 theories compactified on a T2. That's this red region here. There is this green region, which is theories with enhanced supersymmetry. So n equals 3 or n equals 4 supersymmetry. And I've also drawn this, I guess this is a purple color, this region, which are theories where the central charges happen to be identical. And today, for a large part of the talk, I will focus on exploring theories that sit within this purple region, for reasons which I will now explain. So why is this purple region interesting? So let's imagine that our 4D n equals 2 theory has a holographic dual in type 2B string theory. So it has a holographic dual of the form ADS5 times x5. Then, what we all know is that the central charges basically grow like n squared. I haven't told you what n is here, but it's basically the rank of the gauge group or the analog of that. But there are subleading contributions, and the subleading contributions to the central charges have two main contributions. One of which comes from open string degrees of freedom, so like strings stretched between branes. That's typically order n. And then there are closed string contributions, and those come from these kind of R squared terms in the effective action. So if you have two theories with identical central charges, and you want this to happen for all values of n, then it must be such that these coefficients rho and these coefficients sigma conspire in some clever way to cancel. And usually when you see a clever cancellation happening, that indicates that there's something special going on in the physics. So that's something that I will talk about a bit later, but that I think is certainly interesting to understand. This quantity actually, this C minus A quantity, actually controls a whole bunch of things, in which leads to sort of clever and interesting cancellations when they're equal. So I'll just run quickly through this list. So
sorry, can I ask a quick question?
Yes, please do.
If we go back to the previous slide, I guess since you're interested in A equal to C at finite n, wouldn't you say that then you can expand in powers of n, and there are infinitely many terms with inverse powers of n, and so there are infinitely many cancellations rather than just two?
That is indeed a fair statement, yes. So what I haven't told you, of course, is that these rho and sigma have the expansions which you just described. So you can always expand them in 1 over n.
Fair enough.
So indeed, infinitely many cancellations. Thank you. Okay. Yeah. So this quantity controls a bunch of interesting things. So for example, the Carty limit behaves as some exponential in C minus A. So the superconformal index grows particularly slowly if C minus A is 0, for example. It also appears in something called the entropy viscosity ratio bound. It appears in the mixed current gravitational anomaly, and it appears in the single trace higher spin gap for large n. Okay. But nothing I just said was specific to n equals 2, right? Everything I just said actually holds for any 4D SCFT. Right, so I could probably have just said CFT, but let me stick myself to holding at least n equals 1. So it's equally interesting to consider the subspace of the n equals 1 landscape, where you have this purple region where the theories are the same. And this is actually something we did in this the second paper that I mentioned in the introduction, but which I will not talk about very much today. So what kind of theories can you build that sit within this A equals C region? So theories often can be built from a set of simple building blocks. And I'm going to talk about precisely two building block theories, or two families of building block theories today. So the first will be these theories that sometimes go by the name of DPG. These are some non-Lagrangian theories, and their Coulomb branch scaling dimensions are fractional. They're also sometimes called of Argyres Douglas type for this reason. And they've been studied sort of for a long time, particularly by these authors here. And these theories have class S descriptions. And those class S descriptions are a sphere with two punctures, one of which is a regular maximal puncture, and one of which is a so-called irregular puncture. And the regular maximal puncture carries a particular flavor symmetry G, which is this one here. And the irregular puncture sometimes induces an additional flavor symmetry and sometimes not. Okay, so that's one of our building blocks. The other building block that we will consider is called a GG conformal matter. And this is a strongly coupled generalization of just an SUL by fundamental hypermultiplet. I'll explain this a little bit more a bit later on. And this is also a theory with a class S construction. It has two regular maximal punctures now. Remember, each of those carried a flavor symmetry G, so it has a flavor symmetry G times G, explaining the notation. And it also contains one subregular puncture, which is this guy here. It's important to note actually that the word subregular here is is related to the word maximal here, not related to the word regular here. So I could have called this a regular subregular puncture, but that might be a bit of a mouthful. Okay, so I take these two building blocks and I ask, can I construct some 4D SCFTs using these theories as building blocks? And I can think of one way of doing that, which is I take a whole bunch of these things. There's a whole bunch of G flavor symmetries coming from both the DPG theories and the conformal matter theories. And I say, hey, can I gauge all of these G flavor symmetries together? That's certainly a problem that I can pose. You might ask, why is this an interesting problem? But I'd like to answer that once you see the answer, you can see why it's an interesting problem. So I can phrase this entirely in terms of some classification problem. And here's the question. How can we gauge together all G flavor symmetries of a collection of DPG and GD conformal matter such that the result is an n equals 2 SCFT? And it's very restrictive. So let's see how this works. So DPG has a flavor G, and the flavor central charge is like this. And GG conformal matter has a G times G flavor symmetry with flavor central charges that look like this. So this HG check is the dual Coxeter number of the group G. And if you want to consider a conformal gauging, then the one-loop beta function must vanish. And that is equivalent to saying that for all of the flavor symmetries that you gauge together, the sum over their flavor central charges must be 4 times the dual Coxeter number. Okay, so that's the task we have set ourselves now, as to basically solve this equality for all possible configurations of collections of these kinds of theories. And I'm not going to tell you the answer immediately. The first thing I'm going to do is I'm going to tell you about a totally different problem, which is just the 3 branes on an orbifold. This is a very old story, studied in the mid-90s by Cattreau and Silverstein and sort of many other people then and since. So how does that go? So the world volume theory on LD3 branes probing a C2 mod gamma orbifold, that gives you an affine quiver gauge theory. And the ADE type of gamma, which is a subgroup of SU2, just gives you the shape of the quiver. So you see if gamma is ZK, then you have a quiver with K, or K plus 1, probably, no, sorry, a quiver with K nodes, all of which are just SUL gauge groups, and bifundamentals between them in a ring. Okay, so it's easy to ask, what is the generalization of these kind of quivers beyond just considering SU gauge nodes? So if I ask that question, there are 2 things that you look at these pictures and you say, well, I don't know what that means outside of the context of SU. One of them is, what is the generalization of the bifundamental hypermultiplet between 2 SU nodes? And one of them is, what does it mean to take, like, you know, an SU2 and have it be next to a gauge node, which is an SU3? If I replace, you know, SU2 with E8, what on earth is, you know, the thing that goes next to it? So what we propose is, the first one is kind of obvious. The generalization of a bifundamental hypermultiplet is just conformal matter, which is by definition the generalization of a bifundamental hyper. And then we propose that when you have this kind of ramping behavior, that just corresponds to taking a DPG theory and gauging the G flavor symmetry. So let's see how that works. So I can write down these things. These are generalizations in the sense that if I let G be SU, in this case, if I let G be SU2M, G be SU6M, and so on, then these things just become the quivers that I drew here. So in this sense, one can think of this particular collection of things as the generalizations of D3 branes probing an orbifold. Okay. But these are exactly the configurations of conformal matter in DPG that solve the classification problem that I just told you about. That's kind of interesting. There's no other way to combine conformal matter in DPG such that you get a 4D n equals 2 theory. So let's give these theories some labels. So I have basically two pieces of data. I have one piece of data, which is an ADE Lie group, which describes the structure of the quiver, A, D, E6, E7, E8. And I have a ADE Lie group describing the gauge group on the gauge nodes of the quiver. So this is some large collection of theories. And, you know, I would say it justifies asking this question because the answer is ADE. And anytime the answer is ADE, you should find that interesting. Okay. So you could also pose an n equals 1 classification problem. So I told you earlier that, you know, n equals 1 with A equals C is equally interesting. And now the question becomes a bit more nuanced, as I've highlighted in green. So you want to gauge them together in such a way that the result flows in the infrared to an n equals 1 SCFT. That's a slightly different question, because you're free to ask that question at n equals 1. And of course, it's much less restrictive than n equals 2. We studied it in this paper here. And instead of just having nice ADE diagrams, you can have kind of different ways of like tiling the plane with gauge nodes and so on. So it gets rather more complicated. So, you know, as this is some kind of generalization of the ADE classification. Is it something which is known? Is it something which is sort of interesting, independent of this kind of problem? Are sort of questions that we were thinking about when writing this paper. But today I will not talk about the n equals 1 problem and the sort of interest there. I'll just invite you to read the paper. Today, instead, I will first tell you about some features of these 4D n equals 2 theories, which we just said are associated to an ADE sort of structure group and an ADE gauge group. So first of all, some of these theories have identical central charges. That should be no surprise. I led you there by the nose. So that happens in some specific cases. So when there is no conformal matter, i.e. when gamma is D4, E6, E7, E8, as you can see right here, these ones always have conformal matter. And if the greatest common divisor of the dual Coxeter number of G and the largest comarc of lambda is 1, so if they share no common divisors, then the theory has identical central charges. So that's part of the region that we're interested in exploring. Okay, so I told you a lot about class S earlier, so I'm sure you have you're interested in the answer to the question, are these theories inside of class S? Well, the answer is it's not so obvious. And the reason is as follows. So theories in class S can be written by taking 3 punctured spheres and gluing them together along the punctures. Now you see in this picture here, what we've done is we've gauged, so think of this maybe as E6 hat something, E6 hat G. In that case, you gauge together 3 flavor symmetries simultaneously. So this kind of multivalent vertex would not correspond to a pair of pants decomposition of a punctured Riemann surface. Therefore, you know, naively, this thing is not inside of class S. But in fact, that's not the end of the story. It's only not obviously inside of class S. So if you see this 3-punctured sphere that I've drawn here, it contains 3 punctures. So this 3-puncture sphere actually corresponds to a product SCFT. That's something which just happens in class S. No one guarantees that your 3-punctured sphere theory is irreducible. And this theory, in fact, corresponds to 2 copies of the D2 SU2n plus 1 theory, where the class S is of type A2n. And so if you gauge two of these three punctured spheres together by an SU2n plus 1 gauging, then you get something which corresponds to taking 4 copies of D2 SU2n plus 1 and gauging the common SU2n plus 1 flavor symmetry. This is exactly how we defined this theory D4 hat SU2n plus 1. Okay, so this theory does have a description in terms of class S. Of course, what I can't tell you is how this class S description is related to the quadrivalent gauging of two punctured spheres. In fact, I won't tell you anything about that during the talk. But what we will see later is the fact that these theories sit inside of class S is rather interesting. But before I tell you why, I'm going to tell you some other interesting fact. Remember, we're thinking at the moment just about some interesting features of these gamma hat G theories, which I told you about. So the Schur index of a 4D n equals 2 SCFT is defined in this way. And the index is known for theories without enhanced flavor in work by these authors. And so it's straightforward to compute the Schur index for, say, D4 hat G, which is this expression here. So I have to ask, does this look familiar? Perhaps it does, perhaps it doesn't. If it doesn't, I won't hold you for too long. So you can see that actually in each case, you can take the Schur index of the gamma hat G theory, specifically where there is no extra flavor. So now you're restricted to the A equals C subsector. Well, okay, that's not quite true. You're restricted to the subsector where there is no enhanced flavor. So what I say here is true for the A equals C theories, but it's also true slightly more broadly within this class of theories. And what you notice is that you can rewrite the index like this. And this is nothing other than the Schur index of n equals 4 Mills. Well, that's kind of weird. The index of n equals 4 Mills typically looks like this. And you have an extra fugacity for the SU2 flavor symmetry, which is part of the R symmetry, but a flavor from the n equals 2 perspective. And you can see here that basically you specialize that extra fugacity and you rescale the Q, and then you can relate these two indices. So why is this happening? Is this maybe a special structure that's implied by the fact that the central charges are equal? I actually don't have an answer for this question for why this happens, but there is an answer in one case, which is that if you consider the E6 hat SU2 theory, this was studied in great detail by Buikan and Nishinaka in a paper from, I think, a couple of years ago. And they showed that there exists a graded vector space isomorphism between the vertex operator algebras associated to SU2 n equals 4 Mills and this theory E6 hat SU2. Okay, so that's one interesting observation about the Schur index. So let me give you another one. So you can just evaluate the Schur index, at least for small gauge group ranks. And I write it here. So this is the D4 hat SU7 theory. And you see it has an expansion that looked like this. So do these coefficients look familiar? This is the point where I have to sort of forbid Antoine from answering this question as he's seen this talk before. But I have a suspicion that, generally speaking, these coefficients do not look very familiar. In fact, what these coefficients are is they're essentially the coefficients that appear in the Q-series expansion of the generating function of something called MacMahon's generalized sum-of-divisor function. So this is some function that MacMahon wrote down just over 100 years ago. And it's a quasi-modular function, which was shown in this paper by Andrews and Rose, which you would expect as the Schur index is the character of the VOA, and so you should hope that it's quasi-modular. So yeah, this is sort of interesting. So this D4 hat theory, it has a Schur index, which is this rather interesting number theoretic function. And by the way, since the D4 hat theory has basically the same index as n equals 4 super Young Mills with some rescaling, now you have to require that it's SU odd, because I'm considering SU odd here. Then the index of n equals 4 super Young Mills also has this interesting structure of being proportional to the MacMahon sum-of-divisor function.
Craig,
Yes?
do you have a physical interpretation for what we see here?
No, I do not. So there was an interesting paper. Well, so it was an interesting paper which technically appeared on the 1st of April about a connection between like sum-of-divisor functions and n equals 4 super Young Mills and the Riemann hypothesis, which was kind of a cool paper, which may have some sort of connection to the understanding of the physics. But I don't have a good reason for why it's this particular function.
Okay, thank you.
Yeah. Okay. So
can I also ask another question about the previous slide, and where you had
this slide?
Yeah, where you had the specialization of the index of gamma hat. Does this theory have an operator, I guess, that if added as a deformation to the Lagrangian would break global symmetries that would enforce that specialization of the fugacities, or does it not?
I can't say I thought about it specifically enough to answer.
Because if that were the case, then you could think that, okay, you deform the gamma hat theory, and that flows to n equal 4 super Young Mills, right? Something like that.
So
where the SU2 symmetry emerges in the infrared, something along those lines.
So I can't remember the details right now, but I can sort of say a little bit about sort of this one example, which is this where you actually see this graded vector space isomorphism. So you can construct using this isomorphism basically, the map between all of the strong generators of the VOA of this E6 hat theory, which is something called the A6 theory. It was some VOA written down by Fagan, and Tipunin some time ago. This is pointed out in this Buchan-Nishinaka paper. And the key point is that this is not like an isomorphism of VOAs or something. It's much weaker than this. So you don't map like strong generators to strong generators or stuff like this. So I think probably the answer to your question, or one answer to your question, can come from looking at sort of the specifics of this isomorphism of the VOAs, or vector space isomorphism of the VOAs. But I don't have a good answer immediately.
Thanks.
Okay, that was a great time for questions, because now I'm going to talk about something slightly different. So what about the Hall Littlewood index? We just talked about the Schur index. So we can compute the Hall Littlewood index for each of these theories. So the Hall Littlewood index is just defined like this. It's defined as the trace over the Hall Littlewood chiral ring. So the Hall Littlewood chiral ring is given by basically all of the B hat and D type multiplets of the theory. Here I use the notation of Dolan and Osborne, but the notation itself is not so important. And one can compute this thing. There is a so-called TQFT approach by these authors, and one can just compute it. So for the, say, D4 hat SU3 theory, the Hall Littlewood index is this thing. Okay, and if you stare at this, the first thing you notice is that there's a negative coefficient at the tau to the 6th term. And that would not be a problem a priori. But what I just told you was that the D4 hat theories, they can be realized as genus 0 class S theories, right? You take the thing with the 4 twisted null punctures, or the 2 with 2 twisted null punctures, and you glue them together. So this is surprising, because there is kind of a folk conjecture the any class S theory of genus 0 has its Hall Littlewood index being the same as the Hilbert series of its Higgs branch. Where, okay, the Hilbert series of the Higgs branch is now just defined like this. It's the trace over the Higgs branch sector, which I write here, like this. So the difference between these two things is largely that the Hilbert series only goes over the B-type multiplets, and the Hall Littlewood index goes over both the B-type and the D-type. So of course, these things are going to be the same if there are no D-type multiplets in the theory, which is essentially the content of this conjecture here. However, a Hilbert series cannot have negative coefficients. Hilbert series is such that the coefficients are the dimensions of some species of homogeneous polynomials of certain degrees. So this thing that I just told you about, where is it here? This quantity cannot be the Hilbert series of anything. Okay. So we can actually compute the Higgs branch Hilbert series of this theory. And I will explain how in 5 or 10 minutes, but if you just run with me at the moment that we can compute it. It's this thing here. And you see there are no negative coefficients, which is exactly what you would expect. So this D4 hat SU3, which is class S of type A2 with 4 twisted null punctures, is a counterexample to this conjecture that I just presented. And this seems to be something which is generic whenever you have at least 4 twisted punctures.
Craig?
Yes.
So this function that you say here,
Yes.
what is the Higgs branch?
Oh, what is the Higgs branch like as a hyperkähler space?
Is it hyperkähler?
Yes. It's a. Why would it not be hyperkähler? It's a Higgs branch of a 4D n equals 2 SCFT.
It looks. What's so the complex dimension is 2?
That I would have to think about.
The pole at t equals 1 is equal to.
So on a slightly later slide, I will actually tell you what it is. I don't want to flick through and spoil it now, but so maybe I can say it easily. I'm just trying to remember, make sure I get the right theory.
The thing that I don't understand is that in one-dimensional Higgs branches, there is a classification in one of the ADE types. Is it of the ADE? I see you have 2 generators of order 4 and 1 of order 6.
Okay, so you're slightly spoiling the next minutes of the talk. So there are several subtleties, which I can't yet reveal, but later in a few minutes I will tell you the 3D mirror, and then maybe you'll be happier.
Fair enough. Okay.
Okay. But first I want to just give you a few more examples and convince you that this makes sense. So in this paper with Monica, Kihong, Mateo, and Jaewon, we sort of proposed an alternative conjecture that any class S theory associated to genus 0 Riemann surface with at least 4 Z2 twisted punctures has a Hall Littlewood index, which is different from the Hilbert series of the Higgs branch. Okay, so let's see some examples. So I can take sort of the A2 theory with some other twisted punctures rather than 4 twisted null punctures, and we see a -1. I can take it with a lot of twisted null punctures, and again, we see some negative term, order tau to the 6. I can take A4 or A6 with 4 twisted null punctures. Again, you see the minus tau to the 6. And one important thing to note, which one do I want to look at? But let me look at A4 first. So if I look at the A4 now with 6 twisted null punctures, it has a USP4 flavor symmetry from this puncture, and the Hall Littlewood index looks like this. And you can see that there's this negative term. So one subtlety that you have to think about is that if you considered the unrefined index i.e. the one where you turn off the flavor fugacities, then the coefficient of tau to the 6 would be, well, it would be whatever 84 plus 81 plus 35 plus 10 minus 2 is. And that's a positive number. So you wouldn't see this subtlety unless you actually compute the fully flavor refined index. Okay, so I've given you a bunch of examples in the Aeven class S theories, and Aeven are known to be rather special. So maybe I'm telling you something that's a special feature of Aeven with twisted punctures, but I'm not. So let me give you a super simple example. Consider the Dn class S theory with 2 maximal twisted punctures and 2 minimal twisted punctures. There exists an S-duality frame of this theory where it's just a Lagrangian theory. It's SO2n with 2n minus 2 hypermultiplets in the vector representation. Okay, that's nice. We always like Lagrangian theories. Okay, so let me consider the D4 case. I just, work and compute the Hall Littlewood index, and I find this creature here. And again, you can see that there is a minus term, this time order tau to the 8. But again, the minus term still tells you this thing cannot be the Hilbert series of the Higgs branch. But now that we have a Lagrangian description, we can kind of understand this, and here is how. So in this theory, there is not enough matter. We only have 2n minus 2 vector hypers in the vector. There's not enough matter to completely Higgs the SO2n gauge symmetry at the generic point of the Higgs branch. So there is actually an unbroken U1, and that unbroken U1 corresponds to the existence of a D has R charge n minus 1, 0, 0 multiplet. But what did we say earlier? We said that the Hall Littlewood sector also includes D multiplets. So if you have some D multiplets, then these two sectors are different and the indices are different. So in this specific case where I have a Lagrangian description, that's an explanation for why the Hall Littlewood index and the Higgs branch Hilbert series are different. But we don't always have a Lagrangian description. So if it's Lagrangian, you can see it's because the gauge symmetry cannot be completely Higgsed. But what happens otherwise? Maybe we care about these theories that I introduced at the start. So these theories, D4 hat, SU2n plus 1, these are actually rather special. And they're special for the following reason. They're obtained from gauging together 4 copies of D2G. But by this work of Danxi and Yao, they tell us that if you start with the D2 SU2n plus 1 theory and you compactify it on an S1, the so-called 3D reduction, then you have a UN SQCD with 2n plus 1 fundamental hypermultiplets. So that's Lagrangian. So that means that the 3D reduction of this D4 hat SU2n plus 1 theory, that thing is Lagrangian. And again, now if I look at this Lagrangian 3D theory, I see that the SU2n plus 1 is not completely Higgsable on the Higgs branch. Exactly as we just saw in 4D for the SO2n SQCD. And this, the central node is bad in the sense of Coulomb and Witten. So when there does exist a Lagrangian 3D reduction, which is pretty rare, but when it exists, you always see that there is like a central gauge node, which is not completely Higgsable on the Higgs branch. So that again provides sort of motivation for saying that there are D multiplets, and thus you would expect that the Hall Littlewood index and the Higgs branch Hilbert series are distinct objects. Okay, but one of the beauties or joys of this conjecture was that you might want to learn something about the Higgs branch, and in the past you might have said, well, I can compute the Hall Littlewood index. That's something I know how to compute, and I can say that's the Hilbert series of the Higgs branch, and then I'm learning something about the Higgs branch. But in this case, that's not true. So we'd still like to know something about the Higgs branch. So there are a few ways we can do this. So let me take now the 3D reduction of D4 hat SU3. That's this quiver here. It has 4 U1 nodes as lags and an SU3 node in the center. So how can we compute the Hilbert series of this thing? Well, the sort of standard Moline integral approach fails because one assumption is that the gauge group is completely Higgsed, which in this case, we just saw it's not. But in
Sorry,
this...
what do you mean by that? I mean, I can plug in the term equations into Macaulay and
okay.
And calculate the Molian integral. It's just that the naive integrand is not the correct one.
Indeed.
Okay.
That's precisely what I mean. Maybe I should add the word naive somewhere in there. Thank you. But indeed, what we did is you can indeed brute force this thing using Macaulay 2. And you get an answer. You power through all the F term and so on, and you get this thing. Although this is particularly special to this theory that you can sort of have enough computational power to do this in this brute force way. So there are a couple of other ways we can compute the same quantity. The first is that we can, well, okay, so one point to make is that this quiver is bad, which I said, which typically means that there are, how do I say this? Well, okay, so there is this dualization of this theory. And this dualization was for this bad theory, which was once studied by Benjamin Assel and Stefano. And basically around the most singular locus of the Coulomb branch of this theory, you obtain, in fact, this theory plus a twisted hypermultiplet. And this thing here is a good quiver, as you can see, just by counting up the balance. And so this thing you can compute the Hilbert series of using, completely naive Moline integral methods, just following these authors here. And of course, you produce the same answer. Okay. And there's one more thing you can do, which is you can write down the Coulomb branch of the 3D mirror. So the 3D mirror is this quiver here, i.e. it's SU2 with 4 fundamentals. That thing we know very well. The key point is the 3D mirror also includes a free hypermultiplet, which you can think of as coming from the twisted hypermultiplet over here. So perhaps, Hamihai, this answers your question if I tell you that, the Higgs branch around the most singular locus of the Coulomb branch of the 3D reduction is just equivalent to the Coulomb branch of SU2 with 4 flavors. Okay. But in general, the 3D reduction is not Lagrangian.
Yeah, this was, when you have a one-dimensional Higgs branch, you have a very restricted set of options. So
exactly.
What you wrote was the Quiver for Klein before.
Yes, exactly.
Yeah.
But it's sort of important to well, I wanted to first explain that, this is around the most singular locus of the Coulomb branch of the 3D reduction because it's actually a bad theory, and there's some, that's a slightly subtle point. But indeed, it's this thing. Okay. So when the 3D reduction is non-Lagrangian, then, certainly the first 2 of these options are not really options. And so the most sort of potent tool would be to compute the Coulomb branch Hilbert series of the 3D mirror. So we need to know how to do that. So there's been some long-standing program of trying to understand the 3D mirrors of class S theories. And this was done, for example, in this paper of Benini, Tachikawa, and Shi from, I guess, 2011, sounds about right. And they said that if you take the 3D mirror of a genus 0 class S theory of type G is some ADE thing, with untwisted punctures, and I'll specialize to the case of untwisted punctures just to avoid overloading the notation here. Each puncture is basically labeled by a partition, if G is classical, or a nilpotent orbit otherwise. And you gauge the flavor symmetry of a whole collection of what are called TG theories where you Higgs the Coulomb symmetry by the same nilpotent orbit that that defines the puncture. So you don't necessarily need to understand the details of these theories, but these are some 3D n equals 4 SCFTs. And when G is a classical group, then these are all Lagrangian theories. Okay, so that was the case with untwisted punctures. What happens when you have twisted punctures?
Wait.
Mm-hmm.
So do you know what's the answer in case that you have a D-type algebra and two punctures of spinor type?
Yeah, so if you have very even punctures, right. Yeah. So I mean the short answer is no. So if you have basically very even partitions, so a very even partition in fact corresponds to two nilpotent orbits. However, the data of the Lagrangian quiver depends on the partition. And so, you know, somehow you have to write down two different quivers from the same partition. And it's, I think, not currently known how to do that, or what the distinction in the quiver is between the two different very even nilpotent orbits.
My expectation is that the difference will come on the magnetic lattice that you sum over. That there would be some kind of a Z2 distinction between the two.
Yeah, that seems reasonable. So it's not really related to the discussion here, but I wrote this paper recently with Jacques Dissler and Monica Kang. We're in the 60 SCFT context, where you also have Higgsings associated to D partitions. We saw that the difference between the two very even partitions with the same, the two very even nilpotent orbits with the same partition was essentially very high dimension operators on the Higgs branch. So I expect you might be able to import some of the things.
But did you test the volume of the two Higgs bunches? I mean, there is a very simple test. There's a Z2.
Well,
Z2 quotient, one of each other.
Well, in that case, you don't know what the Higgs branch is as you know, as like some hyperkähler space or something. You can compute stuff. Like from the class S perspective, you could compute the Hall Littlewood index. And what you eventually see is that if you go to particularly high order in the Hall Littlewood index, you see that the two start to diverge.
That's divergent.
Sorry?
What diverges?
The Hall Littlewood indices. So at some high order, they have different coefficients.
You have negative.
No. In that case, they were all positive. It's just they are different. Basically, it comes from a different.
By saying
They're
diverge,
different.
you mean not singularity. You mean that
They're
there are
different.
differences. But,
Right. I just mean the spectrum of operators.
yeah. But you just need to give it to Zhengao and he will compute the ratio of the volumes and check whether there is a factor 2 or not. And here's a very simple test.
Can you do it on your phone?
Okay, I will finish the talk. You do the
Yeah,
computation.
let's continue.
Okay, so what happens when you include twisted punctures? In particular, what happens when you include class S of type A even with twisted punctures? So this is something which was studied about a year ago by these 4 authors, including Matteo, who also wrote this paper with us, of course. And what happens is you take the partition associated to SU2n plus 1 and 2 C partitions associated to twisted punctures, and you gauge the common USP2n flavor of these 3 theories. Okay, and this TUSP prime is kind of a quirky theory, but it is what it is. Now, one trick here is that because you have to gauge a USPN flavor out of SU2n plus 1, you have to decompose the SU2n plus 1 into USP times U1. And then there's a leftover fundamental hypermultiplet, which you will see in just a second. In fact, you will see it immediately. So here is just an example. I just took this straight from their paper. So I take A2n with 2 minimal twisted punctures and 1 maximal untwisted puncture. The 2 twisted punctures just give you 2 half hypermultiplets connected to the USP gauge node. And then this long quiver tail here is associated to the TSU2n plus 1 theory, this one here. And this 2 is left over because this 2n node should have had 2n plus 1 flavors, and I only gauged 2n of them, so 1 full hypermultiplet is left over. So this was the state of the art. But what happens if I want to consider mirrors of twisted Aeven, where I have a lot more twisted and untwisted punctures? So obviously having more than 2 twisted punctures is relevant for our discussion of the Hall Littlewood index and the Higgs branch Hilbert series. Okay, so we made a conjecture in this paper that the 3D mirror, where you have arbitrary numbers of twisted and untwisted punctures, is this thing here. So it's very similar. For the untwisted punctures, you take the TSU theories and you gauge a USP. For the twisted punctures, you take the TUSP prime theories and you gauge a USP. And the argument here that gave you, sorry, not here. The argument here that gives you this extra fundamental hypermultiplet, in the more general case, what happens is that you get extra fundamental hypermultiplets, extra anti-symmetric hypermultiplets, and then a bunch of free hypermultiplets. So this is sort of the conjecture for what the 3D mirror is. So obviously this passes all of the checks that you can do easily. The dimensions of the Coulomb and Higgs matches with the dimensions of Higgs and Coulomb. It matches with all of the things where we know how to compute the Higgs branch Hilbert series directly, for example, because we have a 3D reduction. And another sort of interesting thing is that in all of the examples which we checked throughout this paper, the Coulomb branch Hilbert series of this quiver here, it agrees with the Hall Littlewood index at low orders. So before the first minus sign, the first minus sign being where the D multiplet starts contributing. Yeah, so let me maybe elucidate this a bit with an example. So let's consider the A4 theory with 1 maximal puncture, maximal twisted puncture, and 5 twisted null punctures. Then you can compute the Hall Littlewood index, and you find it is this thing here. You can also use the proposal for the 3D mirror. That gives you this thing here. So here I've expanded the TUSP and TSU theories as alternating SOSP quivers. And I see I have 2 anti-symmetric hypermultiplets as well. And I have 2 free hypermultiplets because, as you saw here, there's k-1 free hypermultiplets, and here there is 6 twisted punctures, so k is 3. Okay, and I can use the Hall Littlewood formula of these authors here to compute the Coulomb branch Hilbert series of this thing. And what you find is that it's equal to this guy here. And if you're fast at reading, you can see that these two things are the same, except for this -2 tau to the 6th term. So these things agree at the contributions of the B-type multiplets. Okay, great. Okay, so since it is now exactly 5 p.m., let me conclude. I'm shocked that the timing worked out so well. Okay, so we have constructed some large collection of n=1 and n=2 SCFTs where the central charges are exactly identical without making any sort of large n kind of assumption. And they have the form of a generalization of the affine quivers, and they have some intriguing connections to n=4 Stroup-Yang Mills, such as these relations with the Schur index and so on that I told you about. Okay. Okay, and from this, what we discovered is that the Hall Littlewood index and the Higgs branch Hilbert series is not necessarily equal to each other for genus 0 class S theories. In particular, if you have more than 4 twisted punctures, then these two quantities are different. And we expect this is because of the presence of D-type multiplets, which you can see when you have a Lagrangian way of seeing them. Okay, and because we're actually interested in computing the Higgs branch Hilbert series and understanding the Higgs branch of these theories, we made a proposal for the class S theories of type 2A to N. What are their 3D mirrors with arbitrary numbers of twisted and untwisted punctures? And this now allows us to calculate things like the Higgs branch Hilbert series of, say, these D4 hat SU2N plus 1 theories and so on. I think I actually didn't tell you the 3D mirror of the D4 hat SU2N plus 1 theories in general. It's very simple. I could have just drawn it here. Okay, so let me just tell you very briefly some sort of future directions. So one of the interesting things about these kind of theories, where you have identical central charges, is that there must be all of these complicated or clever cancellations in any supergravity dual. So why do all of these higher derivative corrections, these R² terms, vanish? And it's sort of tempting to speculate there's something to do with fractional D3 branes. But I'm not going to say anything further about that. This is sort of something we're thinking about at the moment. And let me just tell you one other thing. So these theories, in particular, the n=1 theories that I didn't really tell you about, but also the n=2 theories, they have a lot of relevant operators. So you might ask, can I determine larger classes of SCFTs by considering adding superpotential deformations via these relevant operators? And do these flow to new interacting SCFTs? And do these SCFTs, do they also preserve A=C? And you can draw these kind of cool pictures where you start from one theory, as I constructed in the first half of the talk. And then there are a whole bunch of superpotential deformations. This is basically this theory where you gauge the flavor symmetry of DPG, and then you add some adjoint hypermultiplets. And you get this kind of interesting network of superpotential deformations, which sort of follows in a similar structure to those superpotential deformations studied by Intriligator and Wacht for adjoint SQCD some years ago. Okay, I think I'm now exactly 1 hour, so thank you. It was a pleasure to talk here, and I'm happy to take any questions.
All right, well, first of all, let's thank Craig. And spot on an hour, so let's have some questions.
Craig, may I ask you some question, please?
Please do.
Would you be able to identify what's the non-Higgsable sector that give this D-type multiplet? Are that just free vector or?
So I think it is just a free vector because yeah, I think in these cases it's just a free vector. But I'm not sure. Yeah, that's an interesting question. Like there's some terminal singularities on this Higgs branch. Why? Yeah, so we didn't think about specifically what they are. I think in this case it is a free vector. But there may be other cases where it's a more interesting thing. So there are other examples, for example, okay, this is maybe only vaguely connected to your question, but maybe it's interesting for you. So what happens in this example here is that you can go to the not most singular locus of the Coulomb branch, and there the theory is just some free thing. I think it's like 6 twisted hypermultiplets or something. But there are other examples similar to this where the theory at the other singular point on the Coulomb branch, the one of highest codimension, is in fact also some interacting theory. I think we have an example where it's like a 3D n=8 theory. So there's some kind of interesting structure to the moduli spaces of these things. so yeah, it wouldn't surprise me if there were also like more interesting than sort of free vector terminal singularities on these things.
Okay, thank you.
Can I ask another question?
Mm-hmm.
If you go to last slide before the conclusion, where you show the mismatch between Hall Littlewood.
This one here?
Yeah. So for this class of theories, so here I'm showing my ignorance. Is there a Hall Littlewood formula for the Hall Littlewood index? You know, similar in structure to the one that we have in 3 dimensions?
I don't think so. So if there is, I'm also showing my ignorance. But my current understanding is that there is the nice Hall Littlewood formula, which that Hall Littlewood is unrelated to the Hall Littlewood index, except, you know,
because I mean, there are other examples in which, you know, I guess in class S, in which the Hall Littlewood a genus higher than 1, in which Hall Littlewood index differs from the Hilbert series, and you have you know, 2 Hall Littlewood type formula where the structure is the same, but you can see that you know, some factor in the sum and differs, and that's where you know, you immediately see the difference without having to expand at all. So that's why I was asking.
I see. That actually might be something interesting to look into.
Maybe it's a question for the experts.
I hadn't seen it, but yeah, I hadn't seen it. I don't know if Matteo is here. He might know the answer to this.
Thanks.
Yeah.
Okay, do we have more questions? Yeah. Well, if there are no questions at the moment, then let's thank Craig again.
Thank you.
And I'll stop the recording.